Got it. Yes.
Accidentally, originally, you two guys choose the same spot. You want to speak on the same time. I say that Ryan that one. You need to choose one.
Got it. Yes. John McGreevy and I have similar taste, I guess. Boom, 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 boom. Boom, 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 boom.
By the way, how much are you familiar with the things I'm working on? Like, do you know what I'm trying to do? Just wonder whether people are.
I haven't followed very closely recently.
No worries.
But I saw a lot of papers about anomalies. So what are you up to?
Yeah, I have a few proposals to go beyond standard model physics based on constraint from non-perturbative global anomaly and cobordism. And then if you try to use those constraints, there are a lot of not much choice you can play. But once they play out, it's kind of tight things pretty nicely, and it's kind of along the same line of people study ultra quantum matter. You need to put into the correct context, and yeah. So there are several phenomena. For example, like a granular theory, people usually study by its own, or maybe at most study the Higgs breaking from some God scale and break down gauge group. But you can study the transition between different granular theory. And notably, the Patti-Salon and George Glass are two good granular theory, but they have different structures. But if you study the quantum phase transition between the two, there's the possibility to have this emergent gauge field in a critical region, a similar deconfined quantum criticality phenomena.
I see some kind of like deconfined criticality picture.
Yeah.
For grand unified theories.
Granular theory, and except the condensed matter, usually the quantum criticality, the symmetry is internal and global, but in the granular theory, those are gauged. But in the limit that if you treat as global symmetry similar, and once you set up this deconfined like quantum criticality, you can discuss the consequence of gauging the gauge group. And then that anomaly turned out to related to something people study in the context of a 5-dimensional invertible topological order written by Stiefel-Winnie class W2, W3. And that anomaly to match requires some tool we use to match something similar to the new SU2 anomaly. And then there are several tools that build up together, just tied together.
I see.
Yeah, and also I also propose the right-hand neutrino somewhere generation may not exist, but they can carry global anomaly index of Z16. And if you replace them, you may replace it by TQFT sectors or CFT sectors, like Lipschitz multi-type theory. And the reason I think right-hand neutrino may not be there is that people have a difficulty to even identify whether they are Dirac or Marana mass. So maybe the mass mechanism is totally different. And I propose the topological sectors and TQFT and topological defects may contribute to the smallness of the neutrino mass, of the left-hand neutrino mass. And right-hand neutrino mass, usually people use seesaw mechanism to use quadratic mass and Marana mass to live to high energy. But I propose that energy scale can be set out the TQFT gap. And then these are type of things. So the Z2, Z16 anomaly can use that. But certainly I can phrase in a more down to earth way. But this can be very precise. So that's why I try to say the way to be precise. And then the next will be whether I can make any final prediction. But I think it's really, if you really try to explore the phase neighbor to standard model, it can be very messy. It's just like any quantum matter phase, maybe like Cooper, and it may be difficult. But to identify some signatures for beyond standard model physics, I think is highly possible. Anyway.
That would be exciting for sure.
Okay, I think I forgot the time. Sorry for the delay. So let me press the recording. Welcome everyone. Sorry for the delay, and welcome to Harvard CMSA Quantum Math and Physics Seminar Series. It is a great honor. We are delighted to invite Professor Brian Swingle to speak today. Brian previously obtained his PhD at MIT, and then he worked at the Harvard, Stanford, and Maryland, and various places. And his recent research interests lie in the quantum informations and in the context of quantum many-body system and quantum gravity. And today he will be speaking about cosmology from the vacuum. Let me remind the audience, please feel free to ask questions and interact with Brian when you find the appropriate time. So let us directly welcome Brian for yours. Thank you.
Great. Thank you, Juven, for the invitation, for the nice introduction. Thank you all for coming. Nice to see you on this fine spring day. Just came back from a hike. Yeah, so I thought I would talk about a most recent paper from a kind of ongoing, several-year-old now project with my collaborators and I, in which we're trying to sort of make a holographic description of cosmology, something which looks like our own universe, not like ADS, empty de Sitter space. And I want to tell you about the most recent paper which we just put out and some related topics today. For those of you who know me, you think of me maybe as a condensed matter person or a quantum matter person. There is a connection here, which I'll try to discuss, but you can think of this project as me trying to earn my cosmology merit badge. So I'm just having fun venturing into this unknown, to me at least, territory, and we're trying to see what we can do, okay? So the basic idea is, probably most of you are familiar with the idea that there's been this very fruitful exchange between quantum matter, many-body physics, quantum field theory on the one hand, and quantum gravity on the other, primarily in the regime of ADS-CFT, but it of course goes beyond that. And ADS-CFT is really nice from the point of view of quantum gravity because it gives us tractable models of all kinds of interesting quantum gravitational physics. So for example, black holes, scattering, wormholes, all kinds of other exotic phenomena that we'd like to understand better, we get these nice tractable models. But one common feature of all of these models is that the space is ultimately asymptotically empty. That's what the asymptotically empty de Sitter boundary condition means, is that there can be lots of stuff inside, but once you go far away, there's this boundary. And as you approach the boundary, you approach the vacuum. Nevertheless, like I said, there's been this very wonderful exchange of ideas between these two camps. But because of this sort of asymptotic emptiness of ADS, it's remained a very significant open problem to find some kind of quantum gravitational description of physics, of a cosmological physics more like our own universe, where we don't have any asymptotic boundaries that we know of. We have this kind of homogeneous, uniform universe filled with stuff, right? Stuff everywhere, uniformly distributed. So how can we possibly describe that using this holographic kind of picture? Of course, there's no guarantee that it has a holographic description, but what I'll talk about today is one way of possibly getting towards such a description. And like Juven said, I would be very happy to have questions at any time. I'm going to try to keep it pretty basic and just explain the sort of main idea, and starting out with kind of an overview. So what I'm going to talk about really is primarily based on this recent paper. Here's the archive number with my most recent collaborator, Stefano Antonini, who's my PhD student at Maryland, Peter, who's Mark's PhD student at UBC, and then Mark van Remstonk. This paper came out just a short while ago. We'll have some follow-ups coming soon. But in this paper, we basically explore phenomenologically the scenario that I'm going to describe to you in a little bit, and particularly focusing on whether or not you can get phenomenology like accelerated expansion, which is what we observe in the sky today. And the kind of guiding principles throughout this whole approach are that we want some kind of non-perturbative microscopic theory, and we also want there to be a preferred state, a state of the universe in this theory. This is a possibly optimistic hope for the large-scale structure of the universe, but that's kind of the most optimistic thing we could imagine, and we're going to shoot for that, right? The thing I'll talk about today started with earlier work with myself and Mark and a bunch of collaborators at UBC in 2018, where we proposed a sort of, well, I'll describe it later, but a sort of more specialized model of the same physics, where you could get a cosmology living on some kind of brain embedded in the anti-de Sitter space-time. So we proposed that idea, and then that idea has been developed by my collaborators and I, and Mark and his collaborators since that time. And I'll kind of tell you about the most recent iteration of that idea here today. There's also a lot of other relevant works that I don't really discuss in this talk, but just flash a few of them here. There's many more, and if you want to see a more complete listing, you can just take a look at our paper here. So the basic idea is like this. If you look in the sky, data shows that the universe is experiencing a period of accelerated expansion. And the standard explanation for this, or maybe the simplest explanation, is that we have a positive, if small, cosmological constant. Okay. However, you can also explain accelerating expansion with a negative cosmological constant and some time-dependent scalar field. So this is actually, for example, a simple model of primordial inflation, where you also have accelerated expansion. We're not talking about primordial inflation here, if it exists. We're talking about the current observed expansion. But this is totally reasonable from a sort of effective field theory point of view to consider negative cosmological constant, time-dependent scalar fields. They have all the same symmetries. And in that setup, you can, by arranging the dynamics appropriately, get accelerated expansion. So given that this is not really ruled out by data, I mean, maybe the positive cosmological constant is favored, in some analysis of the data, but this negative CC and time-dependent scalar is not, I would say, ruled out. And given that we understand the situation with negative cosmological constant much better theoretically, and we have this prospect in particular of a holographic description, it seems to make sense to explore this possibility somewhat further. Okay, so a lot of work that I'm aware of at least focuses on positive cosmological constant, but here we're going to explore sort of what's possible with a negative cosmological constant and maybe time-dependent scalar fields to mimic the physics of our universe. And we're going to try to use the power of the negative cosmological constant to give us some holographic foothold on our description. But I want to emphasize right off the bat that just having negative CC doesn't immediately imply that you have some simple ADS description. We still want to describe cosmology where we have a homogeneous universe filled with stuff. So there are no asymptotically anti-de Sitter space regions in our physical universe. And for this reason, it's still challenging to sort of formulate a notion of holographic cosmology, because there's no obvious boundary except perhaps in the far future, the distant past, where we might have some sort of holographic degrees of freedom. But what we'll see in this talk is that what you can in fact find in certain models of cosmology is that there are anti-de Sitter space regions asymptotically in complexified regions of the space-time. So you analytically continue time in some specific way, and this gives rise to actually an anti-de Sitter space region, or multiple anti-de Sitter space regions in your complexified geometry. So there was some kind of analytic continuation involved, a sort of duality between two different pictures, one of which you have this ADS asymptopia, where you can sort of try to do holography in a way you're more familiar with. And then in another point of view, you have just more or less conventional Big Bang, Big Crunch cosmology, and possibly even accelerated expansion. So that's kind of the cosmological motivation. And let me just give you an example to kind of ground the discussion. So what I'm showing you here are the two Friedman equations for a homogeneous universe. A is the scale factor, so it just tells you how big the universe is. And I've assumed that I have radiation and negative cosmological constant. And so I've simplified these equations using the radiation equation of state to give you these two equations for A dot and A double dot. And this is a simple problem. It has a known simple solution. If lambda is negative, then you can find a scale factor A such that rho plus lambda, that is the energy density in the radiation, is equal and opposite to the energy density in the CC, in the cosmological constant. And so there will be a turning point. So you start in the distant past of your cosmology down here with a bang. You expand, the universe dilutes. It dilutes enough to where these two terms are equal. And then at that moment of zero expansion, at that turning point, it starts to contract again, and eventually it hits a crunch. So note in particular, there's a time symmetric cosmology here. This is what the scale factor actually looks like. But the interesting thing is, if you go to this moment of time reflection symmetry here, where the universe is at its biggest size, and now you analytically continue time. So you take time to imaginary time. And now you go out, what you find is not a big crunch or a big bang, but actually that the universe grows out into asymptotically Euclidean anti-de Sitter space. So this is the basic picture where you have, on the one hand, starting from this initial slice, if you evolve in real time, you end up with a big crunch or a big bang. And if you evolve in imaginary time, you end up with some kind of Euclidean anti-de Sitter space. And this is a fairly generic feature for this kind of symmetric big bang, big crunch situation when you have negative cosmological constant. And the asymptotically ADS regions in this complexified geometry are kind of the clue that we can have a holographic description of this situation. But it's going to be a sort of unconventional setup. You can already see, for example, there's two anti-de Sitter spaces connected somehow. So there's some sort of Euclidean wormhole here, which connects one boundary to the other boundary. So it's not just going to be described by the physics of a single CFT, but some kind of coupled system, coupled in an interesting way. Okay.
Excuse me, Brian.
Yes.
So is that each time slice all have ADS in this picture along the T?
Along tau, you mean, or along T? Real time or imaginary time?
Real time. So
yeah, it's just a flat FRW cosmology in real time. And then if you go to this time symmetric slice here and then extend in imaginary time instead of real time, then it's asymptotically ADS instead. Of course, there's also radiation in this universe, so it's not ADS throughout the whole space-time, it's some kind of wormhole. But asymptotically, it's ADS. Okay.
But
so,
I mean that
yeah.
When you take a different time, maybe different T, you still get ADS. Is that this is a picture that in each different time slice, the T slice, you still get ADS?
Yeah, if I try to do this procedure at a different time slice in the cosmology, it's more complicated because I don't have this time reflection symmetry. So you could basically, if you want to go in the cosmology from the point of view of the ADS space, you need to do some analytic continuation starting from this surface. So it's not straightforward to just like get slices of ADS, at least as far as I know.
And this solution analytically continue after the Big Bang and Big Crunch.
Yeah. This is a nice analytic function you can see here. It's a known simple solution, and from the properties of the Friedman equation, you can more or less argue that the scale factor is going to be analytic in the vicinity of this turning point, so it at least makes sense locally.
Okay, thanks.
Yeah. Okay, so the question.
Excuse me, I have another quick question. So would you still get that as asymptotically ADS if you assumed it was a matter-dominated universe instead of a radiation-dominated universe?
Yeah, I think so. I mean, the point is just that the negative CC dominates once the scale factor is large.
Okay.
So I think it would work the same. But I haven't thought
Okay,
carefully
cool.
about that case. Yeah, so that's kind of what we hope. Of course, this does have a big bang and a big crunch. That's already nice. It's interesting, but it does not have accelerated expansion in the cosmology. So it's still unrealistic from the point of view of our universe. And one of the questions that we're trying to address, and which I'll show you later, is whether you can get actually accelerated expansion within this kind of framework. But before we turn to that question, I want to describe this setup in more detail and kind of explain to you this duality between the two sides and what I mean by cosmology from the vacuum. So what kind of quantum matter could produce this kind of situation? So here's the idea. We're going to start in Euclidean, so a completely Euclidean theory. We're going to have two copies of a holographic three-dimensional CFT. So that's this top red line and this bottom red line. And they live on R3, so some three space-time dimensional system. And then we're going to take a four-dimensional, typically non-holographic CFT, which lives on an interval times R3, so it lives in this green region in the middle. And it's going to couple CFT3 at the top to CFT3 at the bottom. And what we're going to demand of this theory is that the number of degrees of freedom it has, its central charge or central charge-like object, is much less than the three-dimensional central charge. So it's like you have locally a large amount of stuff at the top and a large amount of stuff at the bottom, and they're connected via a small number of degrees of freedom. This is not elaborate enough by any means, but if you like SYK models, for example, you could think about two SYK clusters coupled by a single wire, something like that. So that's the kind of degree of freedom counting we're thinking about here. And we want to couple this 4D theory to the 3D theory at its boundaries via some relevant perturbation. And we want to ask, what's the fate of this theory in the infrared? And the important point for our discussion here is that there's two ways of thinking about this theory. The first way is if we divide the interval in half. So we have this picture. So we take this slice of the Euclidean path integral. And what this defines, if I open the path integral up along this dashed line, is a quantum state of the four-dimensional CFT in green. It's a quantum state obtained by starting in the Euclidean past with some boundary condition generated from this three-dimensional CFT and evolving that boundary state, that boundary condition, in imaginary time for some amount of imaginary time, W naught. Okay. So it's some pure state, excited state, because we've evolved in Euclidean time for a finite amount of Euclidean time, a pure excited state of a 4D CFT. There's no 3D degrees of freedom at all in this picture. It's just a pure state of the four-dimensional theory. So that's one view of this Euclidean path integral. The other view is if we instead slice it kind of vertically, right? And we then view that as a state in a different theory. Now it's a theory where I have three-dimensional boundary, four-dimensional bulk. This is all just non-gravitational. This is just quantum field theory. But I'm evolving an infinite amount of imaginary time into the past, right? Because it goes on forever. So this is the ground state, actually, of a coupled 3D, 4D, 3D sort of sandwich theory. Right? So we have some actual three-dimensional degrees of freedom on the left, some actual three-dimensional degrees of freedom on the right, and some 4D degrees of freedom that couple them, and we're going to the ground state of this theory. And this is just two different ways of slicing open this Euclidean path integral. And so it's two different points of view on the same Euclidean object. One is this excited state in an infinitely extended 4D theory, and the other is as a vacuum state of this 3D, 4D coupled theory. And the idea is one of these slicing two is going to be our vacuum state, our wormhole vacuum. and slicing one is going to be the cosmology description. And they're going to be related by this duality or this slicing duality of the Euclidean path integral. The fact that these are just two different ways of slicing the same Euclidean theory. Okay, so to get what we actually want physically, to get this kind of wormhole, we need to ask what happens to this coupled 3D, 4D, 3D theory, the sandwich theory. And the idea is that there are roughly two possibilities. So here, now I'm drawing in green the 4D theory, and these two darkened red lines are the 3D theories. And now the sort of shaded red is the holographic geometry associated with those 3D theories. Because remember, those theories are holographic. So they have some kind of bulk that we can define. And if the coupling of the two 3D theories via the green stuff, via this 4D structure, if it doesn't gap out most of the degrees of freedom in the infrared, then what you would expect is just kind of two separate entity sitter spaces that go off and do something. But the other possibility is that these 3D theories are in essence confined or strongly tied together via the 4D coupling. And in that case, you would expect the geometry to be described by some coupled spacetime wherein you can go from the bottom 3D theory to the top 3D theory via this Euclidean wormhole. Okay. So I want to emphasize that it doesn't mean that all the degrees of freedom are gapped, just maybe most of them. There'll still be possibly some light degrees of freedom, like Goldstone modes, for example. But this 3D IR gapped case means that most of the degrees of freedom are of the 3D theory on the top and the 3D theory on the bottom are entangled or correlated together in this wormhole state. So we want to consider this situation. And in this situation, we have this Euclidean wormhole between the top and the bottom. And what we want to ask is, what is the interpretation physically of this wormhole in our two different pictures? Okay. So let's start out with the 4D excited state picture. Remember, this is not necessarily even a holographic CFT. So just think about your favorite, small n conformal field theory in 4 dimensions, whatever that may be. Well, then we have yes.
Sorry, maybe I should ask. Where do you identify the wormhole? Are there some tensor product Hilbert space structure on two sides that talk to each other? Is there some wormhole picture like that? So you say one wormhole?
Yeah, I mean, this is all Euclidean description so far, so it's just Euclidean wormhole. But yes, I have sort of the Hilbert space is roughly speaking modulo, complexities about quantum field theory. It's this top CFT, CFT3, tensor the bottom CFT3, tensor the middle CFT4. Right, and so it's really like you have these two decoupled systems that you're then coupling via this small number of degrees of freedom, this sort of wire system, and that induces an RG flow to a confined state where these two CFTs are strongly coupled together. So it needs to be perhaps be a long RG flow because I have a small number of degrees of freedom here, but there's some RG flow induced which correlates the top and bottom, and that is described holographically via this wormhole.
Okay.
All right.
And the reason you take 3D and 4D, that's because you are taking the space. There's also additional time direction along the time evolution. So that's one direction you skip. Is that right?
Sure. I mean, this construction you can run in different dimensionalities, and that's interesting to do. For the purposes of describing actual cosmology, we choose 4D and 3D because the universe is 4-dimensional. And we want basically to live on this wormhole. This wormhole is sort of where we live actually in the cosmology, as we'll see in a second.
Mm-hmm.
But yeah, the basic construction, if you're not interested in cosmology specifically, that can be considered more widely.
Okay, thanks.
Yep.
Sorry, can I ask a question as well?
Yeah, please.
Yeah, so in the right-hand side, this right-hand picture, the wormhole is eternal, right? It doesn't evaporate or anything like that.
Yeah, it's Euclidean, but yeah, it's eternal. It's extended and
okay. And would it be like I guess we're gonna talk about it later because you said that like this band, essentially the red band, is where we live.
Yes.
Um, would it be right to say like, okay, this wormhole actually exists in our universe? Like, would that be the right thing to say, or?
Well, yeah, I guess what I would put it like this. This is like Euclidean picture. And so there's two different ways of slicing this picture and getting Lorentzian pictures. And we live in one way, we sort of live, quote unquote, in one way of doing the slicing, which is a cosmology. And there's another equivalent way of doing the slicing, which gives you this eternal Lorentzian wormhole. And that's the vacuum state
Okay.
that encodes all of the physics of us.
Mm-hmm. Okay. Okay. Thanks.
Yeah. Okay, so if I come back to the 4D excited state picture, so this recall is where I slice it along in the blue box. So I'm just getting an excited state of this 4D theory. So I'm slicing it kind of along this green line here. Then what happens is once you do the analytic continuation to real time along this sliced surface, the bulk wormhole, Euclidean wormhole, now becomes our cosmology. Okay, that's what I'm representing in this blue kind of crunch, bang crunch sort of picture here. So the analytic continuation in this way gives you cosmology. And according to the path analysis, is just equivalent to some excited state of our 4D theory. If I then do the slicing the other way, as we said, now I'm choosing a different time symmetric slice, and I'm doing analytic continuation along that slice. And now what I get instead of my cosmology is a static geometry, in fact, a vacuum state of some 3D theory coupled over a finite spatial interval to a 4D theory via 4D theory to another 3D theory. And this, again, is the vacuum because imaginary time goes all the way down to minus infinity. So we're cooling effectively this system to its ground state. Right. And this geometry, from the point of view of the bulk, the 3D holographic bulk associated with our holographic 3D CFTs, this geometry is an eternal Lorentzian traversal wormhole. Right. And it's really arising from the coupling of these two 3D theories via the 4D theory. And so the statement of the slice and duality is that this Lorentzian picture can be analytically continued back to that Euclidean picture, which can also then be continued to cosmology picture. So we have these two pictures, the wormhole picture and the cosmology picture, and they're both different ways of looking at this kind of, if you like, underlying Euclidean theory. And in this sense, the physics of cosmology seems to be encoded in the physics of the vacuum in this funny eternal wormhole situation. Now, I just want to comment here, in our earlier work, what we actually considered was a special case where the 4D CFT is itself also holographic. That was kind of an easier case to work with at first. And in that case, if you ask, what is this excited state of the 4D theory? Well, it turns out to have a black hole in its bulk, right? It's itself holographic. So you can imagine filling in the interior of this wormhole with actual spacetime, holographic spacetime for the 4D theory, which then ends on some kind of termination or brane, which is the original wormhole in the 3D hologram. And what you found when you did this calculation is that the state of the 4D theory was dual to a black hole, but it was a pure state. It was a micro state of the black hole. And this so-called end of the world brane behind the horizon of this black hole is where the cosmology lived. But precisely because it was behind the horizon, we generally think of that as being a very hard thing to probe from the point of view of the 4D theory. And so the fact that you have also this ground state Lorentzian wormhole picture of the same physics is really nice, because that's something that we sort of think we understand how to get at. We understand something about how to probe vacuum states in ADS-CFT, for example. We don't have the complexity of trying to see behind the horizon. So it seems to give us non-trivial access and non-trivial control over the physics of this cosmological spacetime, which otherwise is encoded in some very subtle way in a complicated excited state of this four-dimensional theory. So this was the idea that we originally discussed in our paper with Mark and friends in 2018. With my student Stefano, we added charge to this situation and actually showed that you could obtain a situation where this brain had gravity that looked like four-dimensional gravity. So even though it was coupled to a five-dimensional bulk, there were actually essentially localized gravitational modes that behaved just like Einstein's equations would dictate in a 4D universe, except at the very largest scale. So at the scale of the whole universe, maybe the modes could leak off into the bulk, but at the scale of solar systems, say, you could imagine that the gravitational dynamics looks more or less like our conventional 4D world. Okay, so this is the summary. This is the big picture summary. We have this Euclidean 3D, 4D, 3D sandwich theory, as we call it. And that is dual to a Euclidean wormhole. So these dashed lines indicate holographic duality, and the solid lines indicate the slicing duality. So in the Euclidean signature, the sandwich theory is equivalent to the wormhole. And then if we go slice it so that we have this excited state with the 4D theory, that's equivalent via holography to the cosmology. If we instead go to this gapped vacuum state, that's equivalent via holography to a traversable wormhole between two different ADS4 asymptopia.
Hi, Brian. I had a question.
Yeah, please.
So in the previous slide, where should I place the black hole when you were giving this example where the 4D theory is also holographic, so you have an ADS5? And you said that the excited state is actually corresponds to having a black hole?
Yeah, good. This is a Euclidean picture. So you can think of this as, just think of the Euclidean disk.
Right.
And then you have a center point somewhere inside here, and this is the end of the world brain that cuts off some of that space. So when you analytically continue this to real time, it looks like the usual two-sided Penrose diagram, but with a brain on one side, kind of cutting off part of the space.
I guess I was trying to understand your statement that the brain is behind the horizon. So
yeah,
that's what I wanted to.
Let me see if I can I draw. So let me just say this way. There's a point here in the center, which is the Euclidean version of the horizon, and the brain is to the right of that point on the time symmetric slice. So you like go here, you open it up along this slice, extend it into the bulk. So what will happen is the geometry will shrink, there'll be a minimum radius, and it'll increase again, and the brain's on the other side of that. So when you do the analytic continuation, you get that the brain is behind the horizon on the other side of the.
Oh, right. I see.
Yeah.
Okay, that's why you're saying it's behind the horizon, because the horizon is on the left of this, right? If you open it up, it's on the left.
That's right. If you think about old like Randall Sundrum brain world cosmology, which was one of our motivations.
Yeah.
Then the sort of the UV brain is this brain or something like that, and this is like the other side of a black hole, where there's actually some microscopic CFT that's describing the whole geometry ultimately.
I see. Okay, thank you.
Yep. Yeah, so this is the summary. And if I also can talk about the effective field theory point of view, how do observers that live in this cosmology see things? Well, from the Euclidean point of view, so we don't know anything about microscopic CFT now. There's just some effective field theory like supergravity in this Euclidean wormhole. And it's somehow just coupled to this green region, which is our standard 4D theory, but it's coupled in some way to essentially this non-gravitational region. So there's like a non-gravitational region coupled to a gravitational region. But the idea is both of these effective theories, the sort of microscopic 4D theory in some sense, plus this wormhole theory, the effective theory, are kind of small n theories. Like, this is a standard model which lives here, and this is some other variant of that theory which couples the two, right? So there's no large n, CFTs anymore. We've gone to this effective bulk picture, and the effective bulk picture is just the bulk effective field theory on the wormhole coupled to this non-gravitating piece of space. And then we can again do our two slicings. In the wormhole picture on the right, we have our Lorentzian bulk effective theory coupled to this non-gravitational region. And this gives rise to the Lorentzian wormhole, traversable wormhole. Traversability, of course, makes sense because there is a direct coupling between the two sides via the 4D theory. And then if you continue the other way, you have this cosmology picture where you have essentially the 4D theory and the cosmology theory. They don't seem to be connected directly, but in fact, they're entangled in some precise sense. If you actually try to compute, for example, entropy of regions of this theory in this effective field theory picture, then what you find is that you need to include so-called islands in the cosmology that correctly calculate the entropy of this thing. So actually this recent discussion of islands in cosmology is actually very relevant here. And what we find is that you need these islands to properly account for the entropy of this region. So for example, to see that entropy of very large regions of the 4D theory is not thermal, to see that it's a pure state and not a mixed state, you actually need to invoke an island where this 4D theory is actually entangled in some sense with the cosmology. Okay, so we have these two different, very seemingly different pictures. One of our cosmology entangled with this auxiliary bath, and then the other where you have just Lorentzian wormhole between these two different asymptopia.
Sorry, maybe naive question. Can you remind me, how do you identify whether the maybe also the previous slide on this, the holography correspondence, how do you get the gap? Some of the series identify as gapped, while the other is CFT. Can you remind me how do you identify that?
Yeah, good. So I didn't show you any actual construction yet. So of course, I'm just hypothesizing that it's gapped. But what the gap means is that you have these two 3D conformal theories and you couple them, right? And that coupling is relevant and leads to a mass gap for most of the degrees of freedom. As I said, there can still be a small number of light degrees of freedom, like Goldstone modes, for example. But most of the degrees of freedom will be gapped. So think about two large N like holographic gauge theories. You couple them and they confine so that most of the large N degrees of freedom are frozen out. That's the kind of state we're imagining here. And it's a gapped theory because there's a scale, right? There's this length scale here. And if the coupling is relevant, then it flows to an IR theory, which is gapped, and that scale can set a mass gap scale for this theory. Whereas in the 4D CFT case, it's just in flat space, so there's no scale to set. It's just an excited state with some temperature, some effective temperature set by the energy density.
So I had another question, Brian.
Yeah.
So just a very naive question. Of course, the relevant deformation will make it gap, but is that a choice, or do I have to do that to use this duality? The fact that I can slice it two ways, and if I didn't have a gap system, I'm guessing it would not close onto itself. It would not be a circle. Is that
That's
correct?
right. Yeah, that's our picture at least. So I think I would say it's a non-trivial dynamics question. You need to have the right kind of coupling and the right kind of theory to get this to happen.
Mm-hmm.
And Mark in particular, Mark Van Ramsdonk, has suggested very precise microscopic constructions that I won't talk about here. But there are good things to try. And we have not, as far as I know, no one has yet solved, say, the supergravity equations of motion to see if there is actually connected geometry. But that seems like something that humanity can carry out.
Thanks.
Continue the question again.
Yeah.
Earlier you mentioned this random syndrome, maybe the two-brain model.
Sorry,
So how-
which model?
Run-on syndrome
Oh, yeah.
with brain, maybe the UV and IR brain. I don't know how is that related to the picture, what you have?
Well, it's not so related to this picture anymore, but it was this picture here is a version of Randall syndrome to say where instead of having a brain in ADS, you have a brain in an ADS black hole. And if you go through that black hole to the other side, there's actually a true asymptotic boundary where a CFT lives. And that CFT is in a pure state that encodes that entire space-time geometry. So this effective description of gravity coupled to a UV cutoff CFT that RS2 and others talked about is an effective description of ultimately this microscopic CFT that lives on the other side of the black hole, the other side of the Einstein-Rosen bridge. But as I try to emphasize in the construction that we're considering here, we don't really need or even want this 5D bulk. We just want to get rid of that. That was the not necessary part of the construction, and just really think about the situation in which the 4D theory is not holographic.
Maybe also related question again. When you say maybe the two sides of CFT can have a deformation to make a gap, what's a gap size? Maybe in terms of a geometry, can you say that?
Well, I think we would expect it to be set by the length, and possibly like that length certainly sets a scale. The separation between the two sides.
And the smaller size will be larger gap.
Yeah.
Okay. Inverse proportion to the length.
Right. You know, K is 1 over length. Right. So just want to make one point, which is that apart from the holographic story I've told you so far, this whole construction comes with a special state for the cosmology, a state that's defined at the time symmetric point far away from the singularities. And this special state is nice. It doesn't seem to require talking about the singularities at all, at least not directly. And so from that special state at the midpoint, we could imagine evolving forward or backward in time to try to describe the cosmological physics at earlier times, because we don't yet see any bounce in our universe. It's not coming to a stop. So we must be at some point earlier before the bounce, before the maximum size, where it's still expanding. And so we want to describe the physics of that earlier time, and we can do that in principle by starting from this special state at the time symmetric point and evolving backwards. And you know, this has a lot of potentially attractive features. For example, the flatness is just built in as a symmetry. It's just the fact that we're using this R3. The cosmic coincidence problem is sort of natural because at the turning point, the cosmological constant and their matter radiation have to be roughly equal in order for the time derivative of the scale factor to vanish. So this is naturally, you know, if we're living more or less close to the turning point, then this is reasonable. And even the horizon problem is addressed in a non-trivial way, because we have this gapped infrared theory, but if it has, say, Goldstone modes or other low-lying modes that survive below the gap, then those naturally generate long-distance correlations at the turning point, right? So you have correlations on super horizon scales in principle. Now, I'm not saying that these match data. That's a more complicated and interesting question that we're working on. That's an extremely important question. But at least the presence of correlations at long distances is a natural feature of the model. And just to emphasize, you know, the reason for the title is because if you want correlators at this special slice in the cosmology, they're just equal to correlators on the same special slice in the vacuum, right? If you want to go off from that special slice, you need to, of course, do some time evolution, do some analytic attenuation. But on that special slice, you can literally just equate the two of them, right? And so in this sense, the cosmological physics here is encoded in the vacuum physics of this non-trivial wormhole. Okay, now I want to just finish up quickly by addressing this question: can you get accelerated expansion? And I'll show you the answer seems to be yes. This is preliminary, but I'll show you some plots. So what we're going to do here is let's just take the effective theory point of view. So forget about all the detailed CFT stuff. We're just looking for solutions in the cosmology picture, say, for a scale factor and some time-dependent scalar field that's moving in a potential. So we're just going to solve the Friedmann equations and the scalar equation of motion and look for solutions that are time symmetric and exhibit a period of accelerated expansion. If we have those two things, then we're happy. Again, I'm not going to try to make it realistic yet, but we just want to ask the question whether the setup here is in principle compatible with these two ingredients. Okay, and yeah, let me just skip that. So I'll just flash the equation of motion here. I don't expect you to absorb or do anything in particular with these, just to point out two things. That at the turning point, you require that both the scalar field derivative, time derivative vanish and A dot vanish. That's the condition for the turning point. And that will guarantee, or that's the necessary condition for time symmetry. And you see that if you put phi dot to 0 and A dot to 0, then what you need is just to have the cosmological constant balance this radiation term plus the scalar potential at the turning point. So the scalar field has some value at the turning point, and you simply want the potential evaluated at that point plus this radiation term to match the cosmological constant. And indeed, if lambda is negative, then you will be able, in many cases, to obtain this matching. Okay. And the difference between the cosmology picture and the wormhole picture is that essentially the potential is flipped. That's the main feature. And this gives rise then to an interesting heuristic for what we would expect the dynamics to look like. So let's start in the cosmology picture on the right here. And let's kind of imagine going to early time in the cosmology, where we have this period of accelerated expansion that we're looking for. So let's suppose the scalar field is high up in the potential, maybe it's satisfying some slow roll condition. And so we have a period of accelerated expansion because the potential is positive and bigger than the cosmological constant. And so we have some essentially positive CC, effectively positive cosmological constant, which is driving our accelerated expansion. Then as the scalar field rolls down, eventually it reaches a period of deceleration, and as it decelerates, it can actually come to rest at some point here on the potential curve, where now A dot and phi dot is 0. And you can sort of see that actually the fact that there was a relevant coupling is coming in here, because it's guaranteeing that in the cosmology picture that this potential goes down instead of going up. That is, the mass squared is negative, and that's what you would expect for a relevant perturbation in ADS CFT. There's of course a lower bound, the BF bound, that it can't be too negative if we want to have a unitary theory, but it can be somewhat negative. And so you would actually expect from these relevant couplings to have a structure of potential which at first goes down and then goes back up. And so you could indeed imagine this sort of scenario where you start at early time with accelerated expansion, you decelerate, you come to rest. And at that point of rest, that's the time symmetric point, now you can switch over to the wormhole picture here. You invert the potential effectively. And now from that at rest point, the scalar field can just roll out and come to rest at the ADS boundary where you have your ADS asymptotically. So the point of this cartoon is just to try to emphasize that there's a reason to think that this period of accelerated expansion is not just possible, but sort of generic in some sense. I don't want to push that too hard yet, but it looks very natural with these kind of potentials, which start out going down because of the relevance of the perturbation and then eventually go up again, just because, say, the energy is bounded from below, right? That could very naturally give you a scenario where you start with this slow roll region that's accelerating its expansion. You accelerate for a while, then you decelerate, eventually come to rest, and then once you go to the wormhole picture, you flow out to the boundary. So we're kind of using this physics. So it's not just a random construction. We're using the fact that we have this relevant perturbation, and that's giving us, in some fairly generic looking picture, that we could have some accelerated expansion. So what we're actually going to do now, I'll show you one example on the next slide, is we're going to start at this point where we're at rest. And as long as this point is here to the left of the minimum of the potential, we know that if you go to the wormhole picture, you should be able to evolve out to the ADS boundary. There's some condition about the potential needs to be, you know, overall negative out here, but okay, we can take care of that. So what we're going to do is we're going to consider points to the left of the minimum. That's to guarantee that the wormhole picture looks right. And then we're going to type those points, and we're going to imagine, we're going to calculate what happens if we start at that at rest point and evolve backwards towards the past. So we're going to start out going this way, accelerating, or not accelerating, but we're going to start going this way and going up, and then we'll go up, climb up this curve, and eventually we'll reach the Big Bang somewhere up here, or equivalently the Big Crunch if we go to the future. And what we're going to try to find is, we're just going to ask, if I start from some generic phi naught and some generic value of the mass and some other value of the potential. So I just pick the potential, I pick phi naughts. I ask, if I evolve backwards in time, do I eventually get to a region where I have accelerated expansion? And so here is one such result. This is preliminary, I emphasize, it's unpublished, but just thought I'd show it to you here. Suppose you take this potential, it's, you know, not particularly special potential. The -1 is I absorb the cosmological constant into potential. So this -1 is the CC at phi equals 0. So that sets the ADS radius, and I'm using units where that radius is 1, or where that value is 1. And then I have my mass squared. This is going to be negative. And then I have some potential, which is some exponential type potential. It turns out that just a phi 4 potential does not seem to work in this particular setup, but I don't know if that's super deep statement. If you change the potential a little bit, and this kind of potential shows up in string theory all the time, I'm not claiming this is a realistic potential, but I'm just saying this is, you know, not a crazy thing to write down. So then I take these parameter values, m squared is right at the BF bound, g is some value, and phi naught is 0.2, and here is the a double dot, so the acceleration parameter. And you can see that, okay, it's 10 to the -5 is the scale here. So it's decelerating, and then there's a little spike here where it actually accelerates for a little window of time. And then eventually goes back down and starts decelerating again. And then the Big Bang or Big Crunch is very shortly after this final time in the plot. So it quickly goes to, the scale factor goes to 0. A double dot goes to infinity, and the universe has a Big Crunch. So I'm not saying it's a large region. I'm not saying that it's matches the structure of our universe, nothing like that, but it is possible to achieve accelerated expansion consistent with having the wormhole picture and having time symmetric cosmology. And moreover, it is in fact seemingly generic in the sense of being codimension 0 in parameter space. So here again, I'm setting mass equal to -9/4, the BF bound. I'm scanning now over the initial condition and G. And these yellow squares are all the regions in parameter space where I can find some accelerated expansion in my evolution. And if I vary mass away from the BF bound, this little kind of region here shrinks empirically, but doesn't immediately vanish. So it really does look like, as a function of mass squared, G, and initial condition, I have a codimension 0 region where there's accelerated expansion. So it is kind of generic in that sense of being codimension 0, even if it's not occupying a huge part of the parameter space. Okay. So the conclusion is that we can get accelerated expansion consistent with our constraints, and it's even sort of generic, as you might have expected based on this cartoon of the potential that I drew. Okay, so let me wrap up. What I've sort of told you today is what I describe as an optimistic scenario for cosmology, where we have a microscopic control via this holographic construction, and there's a special state that defines the state of the universe. Now, what's interesting from the point of view of quantum matter is that this one interesting thing is that this cosmological history is just encoded in a very complex quantum state of a four-dimensional quantum field theory. This 4D field theory doesn't need to be holographic or large N, but it somehow subtly encodes the cosmological history. And in fact, time evolution in the 4D theory, real-time evolution, is not related to cosmological evolution. The whole cosmology is encoded at time 0 in this state. But at the same time, there's also the Lorentzian wormhole picture where the cosmology is seemingly encoded in the vacuum physics of some other kind of coupled matter. And I want to emphasize this is not kind of the usual holographic duality. It's much closer to recent island discussions where you have cosmology that's sort of entangled with an auxiliary system. And indeed, we can find structures like those islands in our construction. And apart from just the question that I opened with of whether you can have cosmology emerging from quantum matter at all, this approach does offer some intriguing possibilities. For example, we can build in flatness via symmetry. The coincidence problem might have some kind of reasonable explanation. Even the horizon problem, maybe there's hope because we're in the vacuum, which naturally has correlations at all scales if you have massless modes. Because we have that vacuum physics underlying the construction, there's naturally a reason why you would have long-range correlations. Okay, but there's a lot of questions. Two that we're thinking about ourselves are the spectrum of perturbation. So of course we want to evolve back in time and ask what would observers see in terms of cosmic perturbation theory, starting from this special state of the time symmetric point. And could that spectrum of perturbations be roughly consistent or even totally consistent with data? And this is also interesting because it's sort of asking the question about what, if anything, is the role for primordial inflation. Like here I'm describing a kind of mechanism whereby we can get the horizon problem potentially solved from this time symmetric point, not from some early time physics. So is this a dual description of in primordial inflation, or is it an alternative to it? We're not really sure, but that's a very interesting question to think about. It also turns out on the wormhole side that to stabilize this Lorentzian wormhole, you need a large amount of negative energy. And that may sound unusual. Mark and Peter and another colleague of theirs, Alex May, showed in holographic models that you could actually engineer this kind of negative energy. And we're now working on looking at just a free conformal field theory to see if that can also have this enhanced negative energy. Early indications are looking good. So it seems like there's just a very interesting kind of essentially Casimir physics question, like how big can the Casimir energy be given some non-trivial boundary condition? And that's a question that we've been naturally led to by thinking about this construction, but it's really just a question about quantum field theory and quantum matter. Then there's also questions about the role of supersymmetry, microscopic constructions. I didn't talk anything about that, but supersymmetry is presumably pretty important for solving the cosmological constant problem. And the way it's broken in our construction is also important. So that's interesting. And then, even the error of time, like I described things as originating from this time symmetric point, but does that mean the area of time emanates out from that point in both directions or something else? In fact, this is a question we're not sure about, but I mean, one simple scenario is that actually what you have is not arrows of time emanating from that maximum point, but actually sort of counter-propagating arrows of time. And we even have a toy model which realizes that kind of physics. But I think this is still an open question about how to see the arrow of time emerging. It seems to be tied up with the physics of decoherence and other interesting topics in these kinds of models. Okay. But I think that's all I wanted to tell you today. And thanks for your attention. Thanks for the great questions. I'm happy to take more.
Thank you, Brian. Question from the audience? Please feel free to ask more. Each attendee can ask one question. We have many questions. Matthew, please.
Hi, Brian. Nice to talk. how am I supposed to think of this Lorentzian wormhole, the double dual description? I mean, is it like the universe we live in is the one that's expanding and recollapsing, and that's the physics that we see. So this other description, is it just a, like, is there some principle behind the existence of such a well-defined double dual or double analytic continuation that is supposed to sort of constrain the physics we could possibly see in our universe? Or is it just a calculational trick? Or is it the real, that's actually the ground truth, and we're just seeing some kind of hologram of that thing, and that's the actual physics? I don't understand like how I'm supposed to think of this other thing.
Yeah, I mean, this is a good and very complex question. And, you know, I'm of multiple minds about it myself. I don't think we should regard it as the ground truth. Like, I don't think it has more of a right to exist than the cosmological picture. Maybe we feel more comfortable with it because it's not involving cosmology. I don't know, but so from one point of view, it's like a useful feature that lets you calculate in a more efficient way. And you know, and maybe that's not just an accident. It's not just helping me out doing my calculation, but it's really something about how do you access the physics of cosmology. It's saying you shouldn't do real-time calculation in the 4D theory. You should do this analytic continued calculation, this wormhole theory. But I'm also considering the possibility that the fact that it's a proper like Lorentzian piece of quantum matter or quantum field theory is not fundamental. So for example, if you take the case that Stefano and I studied, where you had charge, there was an electric field in the bulk. So when you do the analytic continuation, you get some imaginary terms. So then it's sort of not a wormhole, it's like something else. And maybe it's not even a unitary theory.
So they're in the wormhole picture, the gauge field is imaginary, or it has imaginary components or something like that?
That's right, yeah.
Okay.
So, but then you can start asking, you know, well, maybe this auxiliary theory could be some kind of, you know, non-unitary but still sensible CFT, or some other kind of interesting sort of Statmechy theory that we're using. So I'm not like wedded to it being a totally sensible like Lorentzian theory.
Okay.
But we found that it's interesting to ask, you know, what are the constraints? What can you achieve given that constraint? And you can already get quite a lot.
Right. I mean, it seems like if you want to use a setup like this to solve cosmological problems, then you need to assert that the existence and some properties of this double analytic continuation is a physical principle, right? I mean, otherwise it's just an accident that it exists and then you haven't solved the problem. So normally you don't want that.
No, I think we do want something like that. At least that's the optimistic situation I start. Where there really is this special state that comes from a sensible theory, and that's giving us power over things.
Okay.
Well, I do have many questions, but maybe that's just too many things I need to learn. But let me ask, based on the title, it's called Cosmology from the Vacuum, and vacuum in quantum matter means the ground states. And if I still follow your talk, you are trying to say the time evolution of cosmology can follow from a ground state of some quantum many-body systems.
Yeah.
But then should you still need to give some maybe initial conditions like first order derivative evolution to evolve to encode this information? Or actually you just really read from a single time slot as a ground state? Maybe this is already explained in the talk, but
no, I mean, like if you look at this picture, for example, if you want correlators on this time slice here, they're just literally equal to the correlators in this vacuum state of a piece of quantum matter, so to speak. And more generally, then you would obtain correlations off of this special slice by doing some time evolution in this picture, which would correspond to analog continuation in this picture, right? So it's not like just the equal time correlators in your vacuum state give you all the physics. They give you some of the physics on the special slice, but not all of it. But nevertheless, it is encoded there in some subtle way. That's the claim.
And are those the subtle map is known? Is this solved, or is there still some puzzle you
No,
think?
I wouldn't say we understand in detail. We have a paper that will come out in the next couple of weeks where we show how to, like, suppose you can make measurements at the boundary. So you have access to these 3D degrees of freedom, and you measure, say, the spectrum of excitations. Like you measure the different tower of excitations above the mass gap. Then we show how that can be used to reconstruct the scale factor in the bulk. So we're starting to think about how to reconstruct all the physics of your universe from this, but we're just getting started. But yeah, one starting point to say, if we know the scale factor in the wormhole picture, then we can try to analytically continue that to get the scale factor in cosmology. And so you could actually read out like the size of the universe from the spectrum of perturbations, the spectrum of excitations in your Lorentzian wormhole picture. So like that information is encoded there in some, maybe not even that subtle of a way.
Mhm. And another naive question, just make sure. On the left-hand side, you have this big band and big crunch. The geometry is drawing schematic on the left. On the right-hand side, you have this hourglass shape. Can you just fill me in? Why do you draw this way?
Well, yeah. So this line right here is one asymptotically ADS boundary. This line is another one, and the hourglass is just the shrinking of ADS as you go in, and this wormhole. So it shrinks. There's a wormhole here, and then it increases again. That's why we draw this hourglass shape.
Thanks.
And it's translating in time because it's the vacuum. It's not the size of the space is not changing in time.
Thanks. That helps. Thank you.
Yep.
Any other questions?
Yeah, maybe I can ask. Well, thank you for a very interesting talk. Like some of the ideas are really really cool.
Thanks.
Excuse me. So one of the I've noticed that maybe this is also related to a comment made before, that the appearance of this ADS boundary, essentially that you've noticed from like FRLW cosmology, is kind of specialized, right? Because you have to fix your slice, and you also have to work explicitly with FRLW cosmology, which is kind of simplified, right? Yeah, so I guess I'm just wondering, like, because there are now more complicated models of cosmology that includes radiations of the celestial boundary, so like celestial holography, for example. Yeah, or like even more complicated stuff like maybe loop quantum cosmology. But like there, the notion of time is itself kind of like not clear, at least in loop quantum gravity. But nevertheless, in like celestial holography, would you expect anything similar though, right? Because now you're able to describe like evaporating black holes in the bulk. So now I understand that the ADS stuff is in imagining time, right? But if I imagine, okay, I have black hole evaporating, Hawking radiation, it's completely entangled with like the surface, the boundary degrees of freedom, essentially, right? And I'm allowing the radiations to kind of penetrate out of the quote unquote holographic boundary. So it's no longer unitary. So, well, I mean, first of all, I would not expect like CFT to show up, at least not, in the sense of strong holography, where you essentially you use kind of like a classical CFT data, and then you use that as a fixed boundary condition for the bulk quantum gravity theory. But instead now you have like a dynamical kind of theory where the dynamics of the boundary and the bulk that are entangled. So in that case, so that's I believe that's in real time. By imaginary time, if you Wick rotates, I don't think you would also get like a fixed boundary like ADS or something like that, right? You get something still dynamical. Maybe I'm wrong. I never thought about that before.
Yeah, I mean, it's an interesting question. I also have not thought about it much, so I'm afraid I can't say much right now. But well, okay. I can, one thing I can say, is that from the point of view of, like, if you do have this FRW kind of metric and you don't have the scalar fields, then even if you have matter, radiation, etc., like, it's natural to have the time symmetry. And then once you add the scalar field, okay, that's a constraint that you want this time symmetry, but that's okay. So we can postulate that's a constraint the universe has to satisfy. So it has this nice dual picture. But yeah, then once you're talking about like more like a flat space, yeah, then you could again try to find asymptotic boundaries somewhere in a complexified geometry or something, but I don't know where they would be. I don't know what the interpretation would be. Even here, like if instead of having flat spatial slices, you have curved slices, then the vacuum picture kind of gets more complicated. It ends up being more like a theory on some expanding de Sitter space or something like that. So you can get different kinds of theories besides this simple kind of vacuum theory. And there's still a correspondence, but maybe it's more complicated.
Yeah.
Oh yeah, I think it's interesting to look for these boundaries, but I don't know right now like where they might be in your setup.
Yeah. Well, nevertheless, it's still a pretty cool picture, I guess, to think about, because another question is in one of the plots that you have where you have V and phi, the potential for the, I can think of phi as the dilaton, right? Can I do that, or?
Not necessarily. I mean, here, because I invoked the fact that the mass spread is negative, we're thinking of phi as just dual to the operator, the relevant operator in the CFT. So you have some relevant perturbation to your CFT3, and phi could be the dual field of that.
Okay.
Yeah, I mean, in principle, there could be lots of scalar fields. You can have a complicated potential. This is really like a very minimal cartoon.
I see. Well, I ask because, like, in the example you picked, you sort of have e to the phi squared. That kind of looks like what? Yeah. Well, never mind then.
Yeah, I mean, I'm very, very far from an expert on this, but my understanding is that for like moduli parameters, for example, these kind of potentials are fairly generic. So yeah, that's the like you open some string theory paper and someone writes a potential involving 20 terms of this type, and so we just sort of took a little inspiration from that and tried something simple.
Okay. Well, thank you.
Yeah, thanks.
Okay.
Great.
No more question. That is directly saying, let's thanks Brian again.
Yeah, thanks a lot.
Right.
Good to see you, Juven.
I'll send you a video link. Thank you.